Thank you all for coming tonight. Is this still working? Okay. It's great to be back. This is my third time doing Volcano Awareness Month talk, and I really enjoy engaging with you guys, so I hope you enjoy this talk. It's a little different than past years just because, as the title says, this year was quiet but insightful. So we're going to have a very quick review of kind of where we are and what Kilauea has done in the past, and then we'll talk about some things that my colleagues and I have all been working on together. So there are slides from multiple other people's presentations in here that I've kind of put all together, and while my name is on this, it's certainly everybody at HVO who's contributed to what's in this talk. Okay, so we are here on the Big Island of Hawaii. We are up here at the National Park. Our island is made up of 5 volcanoes. For those of you who are visiting and may not know, this is Kohala up top, Mauna Kea with the telescopes, Hualalai, Mauna Loa, which is our largest volcano on the planet, and Kilauea, where we are. We also have Little Loihi down here, submarine volcano, and it's going to stay under the water for quite some time, so don't worry about seeing that one. These are all basaltic shield volcanoes, which means that they are not your typical conical cone that most people think of as a volcano. These are broad shield volcanoes, and they're classic in their own right. They typically have rift zones. In our case, they have 2 rift zones that come off of a summit caldera, and we have an east rift zone that stretches all the way out here, and this is what we'll be talking about today. And we have a west or southwest rift zone that comes down here. Under Kilauea, we have at least 2 magma chambers, the Halemaumau shallow source and the South Caldera deeper source. And along the rift zones, this is going to come into play in our talk, there are these little stored areas of magma throughout the whole rift zone, and we'll dive into that a little later. There's also 2 major fault systems on our volcano here. The Kīlauea fault system, which links the upper east rift zone to the seismic southwest rift zone, and the Helena fault zone, which basically is the part of the edge of the south flank that moves on our volcano here. Okay, so this is a very abridged eruption history of Kilauea, and for those of you who are diehard fans of Volcano Awareness Month, it's going to be just as odd for you as it is for me to summarize Pu'u'o in one slide. But we're going to do it. So a brief history of what Kilauea has done, kind of setting the scene a little more for what happened in 2018. In the past 70 years, we started with a 1955 eruption labeled here, these 2 gray spots. That was followed in 1959 by the Kilauea Iki eruption up here at the summit in December, and then the next month in January 1960, the Kapoho eruption happened down here on the lower east rift zone. LERZ stands for lower east rift zone, and this is upper east rift zone here. So through the 60s, there were multiple fissures, roughly 1 a decade, not quite. Some years had 2 and some years had none, but roughly 1 a decade, fissure eruptions on the upper east rift zone towards Mauna Ulu. And then in '69, Mauna Ulu started erupting with some lava fountaining through the rest of that year. It lasted another 4.5 years till 1974, all effusive lava flows. There was some little fountaining here and there, but no major episodes of that. There were then some fissure eruptions in the middle rift zone here and the upper rift zone between 1974 and 1983. But then in 1983, we started 3 years of 48 different lava fountaining episodes that became the Pu'u'o eruption. There was another 32 years beyond that of lava effusion, and that made for a 35-year-long historic eruption. That was joined at the summit by a 10-year-long lava lake that started in 2008. But as you can guess, 2018 stopped both of them. So those eruptions have ended. 2018 was historic in its own right, and we're going to get into that tonight. So the first day of leading up to the eruption, the first day of precursors, was April 30th, 2018. Pu'u'o, around 2:15 p.m., had this massive swelling or inflation, and then it collapsed on itself. So this is the cone. And it made this typical pink ash plume for many days that week and several weeks after. That inflation that happened for about 15 minutes cracked the west side of the cone. And it was pretty rainy that day, so we couldn't see anything on our cameras. The thermal camera caught a little bit, but we ended up taking a helicopter out the next day to see what had happened. This was a huge signal that had never been seen to that magnitude here before. So here's a video from the helicopter. This used to be filled with lava. You couldn't see down here, and when we took this helicopter flight, we couldn't see the bottom of this hole. It was at least 500 or 600 meters deep, and there's some little dust that sloughs off, and it just keeps going. You don't even see it rebound when it hits the bottom. It was very deep. It has since filled in with talus, but that was our first clue when this collapsed that something was happening, and then seeing how deep and how big this scar was inside the crater was really eye-opening. So I'm going to talk about this plot first. This is the rest of the afternoon of April 30th. After about 2:30 p.m. there was earthquakes that started migrating down rift, and typically a lot of our activity for the past 35 years had been in this middle rift zone at Pu'o or somewhere in the upper east rift zone connector. But on this day, whatever happened at Pu'o, whatever failed underneath it, allowed magma to move forward down into the lower rift, which is down here. On May 1st, we see that earthquake front migrating to the east. And then on May 2nd, it stops just short of our station WAPM, right under the subdivision of Leilani Estates. And to give you a sense of what this image is, it's derived from what we call INSAR. It's a satellite that passes over and measures, it can measure very fine movements of the ground. Typically you see it as a colorful rainbow image, but this has been processed such that you see subsidence in blue and inflation in red. And these are in millimeters, so these are not huge distances, even though they look very dark blue. But it gives you a sense that during this 3 or 4 day period, the entire middle rift zone and part of the upper rift zone was losing material in the subsurface to the lower rift zone, which was becoming engorged. The other thing that started happening on May 2nd was that surface streets in Leilani Estates began to crack. And at first it was 1 crack, and then it was 2 cracks, and then it was 5 cracks, and then it was 10. And we realized this is going to happen fast. And again, the ground is swelling up as material is moving under Leilani Estates. The next day, on May 3rd, we have some more earthquakes in the same area. And Fissure 1 opens that evening around 4:30 p.m. It crossed Mohala Street, and this is what it looked like. You can see it's already starting to make a lava pad, but that pad's not going very far. It's only going a couple of feet. It's actually pretty thick, maybe 2 or 3 feet tall. And this is what you would call a classic fissure. It's a line a crack that erupts magma, and there are multiple sources of gas pushing the magma out of this crack. So it's pretty sluggish. It's not what we typically think of from the Pohoihoi from Pu'o. This stuff isn't going very far. But it's also in a neighborhood, so that's a good thing. It's not going very far. The next morning, literally at 1 a.m. the next morning, Fissure 2 opened, and the next few fissures, all the way to Fissure 6, opened sequentially down rift, right to about where the earthquakes had stopped progressing forward. In the middle of all of that, on May 4th, we had a magnitude 6.9 earthquake that was felt throughout the state, and while it shook a lot of us, and especially those in Puna, it didn't seem to affect those 6 fissures that were opening up, or those 5 fissures that were opening up that day. They just carried on with their sluggish spattering as if nothing was wrong. During this earthquake, the entire south flank of Kilauea moved. This is another one of those INSAR-derived diagrams. 150 millimeters is 15 centimeters, so that's everything from this line and down moved at least that much, if not more. On May 6th, after Fissure 6 was done erupting over here, Fissure 7 opened up the next morning, right next to Fissure 2, And then the vents started opening up back uprift, with the exception of 12 that jumped the line and went back downrift. But in general, the trend was an uprift migration. Here's a video of fissure 11. I turned the sound off on this one because all you hear is a very loud helicopter. You can't hear the fissure at all. But again, it's very sluggish, perhaps a little more vigorous spattering. You can see that there's multiple spots, but they're all kind of red together instead of individual red spots. But it's lava that's not going very far. It's very sticky. It's very viscous. There were 2 days of pause, May 10th and May 11th, where we thought, is that it? Are we done? Or is there more coming? And we assumed there was more coming because the earthquakes started migrating down rift again. And they didn't go that far down rift, but they went far enough that we thought, okay, the next fissures could be down rift. And sure enough, fissure 13 opened here, 14, and then the rest opened sequentially down rift. Fissure 17 is offset. It's the only one offset majorly on the whole trend. And here's a video of what that looks like and sounds like. So that was a cannon shot sound that it was making. And at the peak of its activity, it was doing that every 5 to 10 minutes. And you could hear that for several miles away from the fissure. This was very interesting fissure because not only was it offset, but it was erupting a slightly different composition, which we didn't know up front, but we assumed something was different because none of the other fissures were making this feature. We'll talk more about the chemistry of this later in the talk, but essentially this is a more evolved basalt, basaltic andesite, and this more explosive area was just an andesite. There was no basaltic component to it, it's just andesite. May 14th to 18th, the rest of the fissures up through fissure 23 began opening uprift again. So the thought is that the earthquakes came down, something was preventing them from moving further. The dike was able to kind of fill that crack that they had created and erupt in here, and then the earthquakes were able to break open the rock and free up some more space, and the magma moved down here. Once that couldn't move forward anymore, it starts filling up and backing up uprift. Fissure 24 over here opened on May 27th, and that was because of a series of reactivations that finally went from fissure 17 all the way back to fissure 8, and it reopened, or fissure 24 opened for the first time when fissure 8 reactivated for its big show in June and July. So this is a slide that one of my colleagues made showing seismicity in the lower East Rift Zone, the south flank area, and the summit. And the key thing I want you to take away from this slide is that all of the seismic activity for the lower East Rift Zone happened in those first couple days in May, from April 30th to May 18th. And then everything kind of went quiet on the Rift Zone. There was still some activity, but compared to what we had just seen on the lower East Rift Zone, it was relatively small. And all of the seismic activity, as you can see, went to this blue area, which is the summit. So we're not going to talk about that part today. We're going to just focus on the lower rift, but the deformation also did the same thing. This is based off of INSAR data again, and while it shows a general subsidence across the entire East Rift Zone, it's very small. It's 2 centimeters, it's 1 inch. Whereas the previous slides we were seeing multiple inches of change. It's all kind of a wash in here. So the interpretation that we came to eventually was that if there's no geophysics, which usually means the eruption's ending, and yet we still see lava coming out, and it's actually coming out more and more vigorously and faster, what does that mean? It probably means the conduit is quote-unquote open. There's no more resistance for the lava to flow and try to break rock to get to the surface. It has a path from wherever it's coming from in the rift zone or the summit, and it has a clear, easy path to fissure 8. So here is, well, I should say fissure 8 or some of the other fissures that rejuvenated right before fissure 8. Here's a video of fissure 20. This is our second fissure to show classical Hawaiian fountaining from a fissure source. Let's see if this will play. So again, you have multiple fountains along a single crack, erupting magma that is producing a lava flow that is moving quite moving quite quickly down from fissure 20 and around into a subdivision. And it covered this area, which is probably a kilometer or a little more in distance, within minutes to an hour. It was moving very fast. So much so that the helicopter pilot and I actually got out on one of these side roads at the cul-de-sac, and I called civil defense, and he went and warned a few people who were still home that they needed to leave because this was coming at them very quickly. All right, so from May 18th, when our geophysics kind of goes quiet on the lower rift, to May 27th, right, as fissure 8 reactivates, we have a series of uprift reactivations. Fissure 17 on May 18th, 19th was going strong. It had an 80-meter tall fountain. Fissures 16 and 18 were also active. 20 and 22 were starting to send their flows down to the sea. They did that in a day and a half. As fissure 17 started to shut down, fissure 19 and 15 started to reactivate. And then I noticed as 16 and 18 appeared to shut down, turns out they never quite shut down, but as they decreased activity, fissure 6 and 13 started to increase activity, and they produced a joint lava flow that also went to the sea. And then as fissures 20 and 22 started to shut down, 23, 21, and 7 started producing a flow, and 21 and 7 together sent a flow to the north towards our geothermal plant and to the south. I think had it not filled this pit crater here, it would have reached the sea as well. But quite a bit of volume went into this pit crater first. And then as everything else shut down, 6, 13, 23, fissure 8 reactivated on May 27th. And with that came the new fissure 24. And once that started flowing and effusing a lava flow, fissures 7 and 21 just shut down as well. During that time of reactivation, as the lower vents shut off and that pushes magma to come out of the next available upper vent, we saw what's called a graben form. And that is, if you think of a keystone in an archway, a graben is essentially that kind of a shape, and it drops down as magma ascends. This one is fairly small. It's 100 meters, or a football field across, but it dropped about 2 meters, or a little over 6 feet. Over the course of 2 or 3 days. And the reason that these grabens form is when magma is trying to rise, it has to push the walls apart. And so just like a keystone helps keep a doorway intact, the ground surface will drop and behave in much the same way as it's being pushed apart, so the lava can reach the magma can reach the surface. I should mention, that this is LiDAR based, because this is a little too fine scale for the INSAR-derived image, but you can kind of get a hint of it. There's a few blue spots in the same trend there. This, like I said, this was 100 meters across, 1 football field across. It was several kilometers long. It stretched essentially from Pohoiki all the way to Highway 130 through the whole subdivision. So here's what that looks like. Over the course of a little more than 24 hours, and prior to this, it had been just a hairline crack, turned into a 1 or 2 foot crack, and 6 inches, 12 inches of down drop to 6 or 8 foot wide crack and 3 or 4 feet of down drop. And like I said, it ultimately reached about 6.5 feet of down drop. This happened very fast. Actually, the residents stopped me in the middle of one of my shifts and say, "Is the ground sinking?" Yes, actually, the ground is sinking. That was our cue that a lot more magma was about to come out of whichever fissure it chose as the easiest path. That was fissure 8, and it was active for 2 months. It started, its first rejuvenated flow May 27th. It lasted until August 5th. In this picture, which was taken a month into that time frame on June 26th, you can see how long and how wide it is. Right here, this red line is a ½ mile wide, or 800 meters across. The flow came up Luana Street and then made a bend to the northeast here in this picture. It went 8 miles, or 13 kilometers, until it reached the sea, and it did that in 5 days. So the average eruption rate for those 2 months was approximately 100 cubic meters per second. And to put that into terms that we might recognize for those of you who've come to these talks a lot and think about pu'uo'o a lot, Fissure 8 erupted 5 years worth of pu'uo'o material in 2 months. And that works out to about a cubic kilometer of uncorrected, diffused material. So we haven't corrected for the density in that. But Fissure 8 wasn't done, even though the channel drained. The effusion rate dropped dramatically on August 4th. The channel drained on August 5th, and there was still a little bit of lava inside the cone from August 6th to 15th, and there was still a few ooze-outs and ocean entry tows as well during this period. But there was nothing in the channel by August 6th. And then lava went away for a while. And so again, we're asking ourselves, is this it? Is there more coming? Is this just a break? How will we know? And lava came back one last time, September 1st to 5th. And it was very weakly active. It stayed within the Fissure 8 cone. And this is a video showing, just how weak it's spattering. There's a nice breakout here with the crust being pushed off. But it didn't make it into the spillway. It didn't reoccupy the channel. And then it drained away as quietly as it came back. And that was finally the end of the eruption. So that brings us to 2019, which is what this talk is usually about, the past year of what's been going on. And we can summarize it in just 1 or 2 slides because thankfully it's been quiet. But the unfortunate thing is that some residents are still feeling the thermal effects of the intrusion. As the dike is trying to cool, the heat is moving into the surrounding ground. So this is one resident's property. There's a breadfruit tree right here. That was the first crack on this particular resident's property, and it was also the first steaming area. We thought this was actually going to erupt at one point because it had a blue tint to it, which means there's sulfur mixed into that, sulfur dioxide mixed into that. But it never erupted. However, a year later, this is the same breadfruit tree. All of her vegetation has essentially been boiled and dissolved away by the groundwater that is so hot from this intrusion. So you can see it used to be a very nice lush green field, and by the time we took this picture, parts of it had died. But now the plants literally just fell on the ground as their roots boiled, and then they dissolved themselves. And it leaves this little white crust behind on the rock. So those residents are in Ala'ili, and they've been feeling this for the better part of a year and a half now. This started for them during the eruption. They saw it progress through the eruption, and it's just been getting worse after the eruption. But recently, Halekamahina residents have called us and said they started noticing some similar effects that we recognized from Ala'ili this fall, so for the last 5 or 6 months. And then Leilani Estates called in December and said, hey, folks next to fissures 9 and 10 are noticing the temperatures on their property are rising. Is everything okay? And the unfortunate answer is yes, everything is okay, but here's what's happening. Well, here's the areas that are affected. This is the Ala'ili area. This is the Leilani Estates area that was recently affected, and this is the Halekamahina area. So, in our geologic cartoon, we have a dike that's coming up to the surface. It doesn't break the surface in this cartoon. It's just an intrusion to help conceptually with the process. Thermally, right above the intrusion is very hot, magmatic temperature hot, hot steam coming out of this crack. We're talking anywhere from 2 to 500 Celsius. So very hot, much higher above the boiling temperature than anyone would want to approach. But just a few yards away, 20, 30 yards away, the ground feels normal, feels cool. It doesn't feel hot at all. It's just these cracks that are really hot. But fast forward, whatever time frame you want, 6 months, a year, this heat will slowly start leaching into the ground rock, and this spot will cool down, but these spots will warm up. And so this has basically cooled to the boiling point. It seems to be buffered there. We haven't seen the temperatures change on these properties above or below the boiling point too much. But now that 20 yards away that used to be cool also has steaming water and is just shy of the boiling point. And that's because the heat from this dike is slowly migrating outwards into the ground as this tries to solidify and crystallize. But unfortunately, that means that farther areas away that you thought wouldn't be impacted at all by the heat are now starting to warm up. And so a lot of residents in these affected areas are asking themselves, well, is there anything we can do? What should we do? And unfortunately, our best guidance is the 1955 eruption, where there were steam vents that were still warm and spa attractions as recently as 2018. So it can stay hot for several decades. And that's just how the heat is trying to leave the dike so that it can solidify fully. As I mentioned at the beginning, this eruption was unprecedented for Kilauea in the past 200 years of its activity. The total flow field area, which is in pink here, was 13.7 square miles. The new lava delta area, this is the old shoreline that's dashed here. So this area that extends out into the sea is 875 acres. I think that's all I wanted to say on this slide. It was the most voluminous eruption for 2 months of time in the past 200 years. Pu'o'o did erupt more volume, but it was over 35 years. It's the highest sustained lava discharge rate ever measured from Kilauea, and it's the highest SO2 rates measured at Kilauea. In addition, the 6.9 earthquake was the largest we had had since 1975. So let's talk about the gas for just a slide or two here. Our gas team started measuring SO2 output from Kilauea in 1979, and when the Pu'o'o eruption started in 1983, we averaged about 1 megaton or 1 million tons of SO2 per year. When the summit eruption and the lava lake started in 2008, that bumped up to 2 to 3 million tons of sulfur dioxide per year from Kilauea. However, you can see this giant bar over here on the side of the plot, and that is solely 2018. And that is solely from the lower rift zone. When that eruption started in May, and especially as it picked up in June, the other summit and Pu'o'o areas basically dropped to zero sulfur dioxide output. It was within the noise, so we weren't sure if we were actually getting a reading or if it's just within the noise. So 10 million tons of sulfur for the year came out of Leilani Estates. And 2019 is down there. 13,000 tons for the year. Much reduced. We've had the best air quality on this island that we've had in a long time, and that is the lowest rate since these measurements have started being recorded by our gas team. There we go. Okay, so that's kind of the summary of the past year and the 2018 eruption. Very short and to the point. HVO's been using this quiet year, A, to move into our temporary facility, but B, to start addressing some of these questions and gain some insights on what happened and why, and try to find some answers so we can understand future potential eruption crises better. So we touched on this one already. What does it mean when the seismicity and the deformation stop, even though the lava is still flowing? It means the conduit is open and that there's likely more material coming. Until we see some other sign like the gas drop or the lava just stops coming out. It's really a fluid dynamic and a magma static head that's continuing that material to erupt. So how does magmatic chemical variation affect eruptions? Because it's not, this first point is really about the structure of the volcano, but it's that there's more that controls an eruption than just the structure. There's also the chemistry. And this work, I've taken a few slides from our colleague Cheryl Ganzecki at Hilo. She did a fantastic job during the eruption with her colleagues and with HVO, essentially doing petrology real time. She kind of pioneered that with the proof of concept in this eruption. So let's look at how different chemistries affect what the eruption does. And this is a repeat from her talk last Thursday night. If any of you were there, you'll recognize a few of these slides. So again, we can look back to the 1955 eruption that was in the same area. So our 2018 eruption was kind of in this gap right here. They noted in 1955 that the lavas seemed cool and that they might have been stored for a while. They had some more crystals, they're sticky and viscous like our first 15 fissures were in 2018. The lava produced later on in the 1955 eruption was more hot and fluid and covered a lot more area, as was the case in 2018 as well. So we're back to these little pods of magma that are stored in the rift zone. And why are they stored there? Well, any eruption that happens never erupts 100% of its material. There's always something that's left behind. And depending on how warm that something can stay, it could be remobilized later. So we call these magma storage regions. There's one under Makaupuhi crater that drained during this event. And there are probably numerous others that we don't even know about, but there are a half dozen or so that we do know about. It's likely residue from earlier eruptions, and for the 2018 eruption, the chemistry seems to match an evolved 1955. So the 2018 material came in, but to get out first, it had to push out what was left of the 1955 magma. So when the magma is in the rift zone, it's not, without an intrusion to help push it along, it's not going to erupt again on its own, which gives it time to cool and crystallize and solidify. But as we know, since we evolved 1955, that process can easily take 7 decades. That's how long this has been sitting there, and it came out again. All right, so here's one of Cheryl's chemistry plots. Don't be intimidated, it's actually really easy. So she's looking at calcium oxide as a proxy for temperature. So she's measuring this, and she can determine the temperature of the lava that it erupts at. So fissures 1 through 15 here in the yellow all erupted pretty cool for Kilauea, so around 1110 Celsius. Normal composition from Pu'u'o just a month prior to this event is up here. So this is kind of cool, a cooler temperature. Fissures 16, we're just going to skip 17 for a second, and 18, 19, 20 were a little warmer. And as you remember, that was as we started to turn the page from sticky magma into more fluid and less viscous magma and hotter magma. And then when our geophysics kind of die away in the lower rift, we start seeing lava temperatures that are much hotter. They're not quite Pu'u'o temperatures, they're just shy of it. And that remains true for the rest of the eruption when fissure 8 turns on and for the whole time that was active. So why is that a little cooler than Pu'u'o if we think Pu'u'o material is actually coming out at this point? Well, it has to travel twice as far, so it's going to lose just a fraction of its heat in that transit underground. Now, fissure 17. Let's talk about that. So that erupted really cold for lava, especially from Kilauea. Fissure 17 did that. This is the initial fissure 17 samples. Later in its life, before it totally waned away, it did warm up a little bit. But this is, again, because of that chemistry issue. This is evolved 1955 basalt that's getting pushed out. This is basalt that we're used to seeing from Pu'u'o and maybe even a little bit from the summit. But this is basaltic andesite and andesite. It's just naturally a slightly colder magma. And since it's sitting in the rift zone and we don't know from what eruption it came from, there are some options, but I'm not sure that Cheryl and her group has pinned it down yet. The magma is not only cooling, but it has time to evolve. As crystals form, they leave behind the silica dioxide, and that's the difference between a basalt and an andesite, is how much silica dioxide is in the liquid rock. The more silica, the more viscous it is. The more viscous it is, the more explosive it is. So new eruptions can push out the older magma, but it does come with the consequence of potentially increased hazards. So that's our insight number 2. New magma types can lead to new eruption styles, like the big explosive boomer that you saw and the canyon shot that produced. But it also comes with the hazards that produces, where lava bombs are flying much farther than they otherwise would have. And this is a slightly denser rock. It punctured through a roof, I believe. and a wall, and unfortunately broke someone's leg. So it has some extra hazards that you wouldn't think of for basaltic eruptions. Okay, next question. Why did the Fissure 8 fountain pulse? Matt and I and many of our colleagues noticed that several of the fountains, but especially the Fissure 8 fountain, was sitting there doing its thing, but it would go up and down on like every 5 to 10 minutes. And the question was why? What is that all about? So the next few slides are from Matt's talk from last year and some of his new work that we co-published together this year. So this is a video. He sped it up 5 times. This is courtesy of our UAS team that was here during the eruption. They are USGS, not HVO specific, but they were a huge help in monitoring the eruption. And you can see that at times Fissure 8, which is here, is sending a lot of material through this spillway into the channel, which starts about here. And we're getting some convection, it looks like turbulent flow. And then after 5 or 10 minutes, and remember this is sped up, so it's going to be a few seconds here, it slows down. And we start seeing more crust, and we lose our turbulent eddies, and they're almost all gone except for that one. And it stays like this, nice and calm and flowing a little more slowly. And then it'll speed up again. And Matt finally wrapped his head around it and was able to figure out that this is very similar to a process that we've seen before called gas pistoning. The only difference is that gas pistoning, when we've seen it at Mauna Ulu and at Pu'u'o and at Halemaumau, it's confined. It's in a pit. And so you see the lava rise up, and then when the gas can finally break the surface, the gas all comes out and the lava drops back down. And so it's a cyclic rise and fall of a lava surface depending on the gas buildup and the gas release. But if you're in a fountain that has a spillway where lava can leave and it's not confined, it manifests itself a little differently. So as Matt was able, after watching hours and hours of video and tediously analyzing it, he was able to figure out that as the fountain height goes up, more SO2 comes out of the fountain, so our gas flux goes up. And the seismic tremor goes up. Keep in mind, this is all smaller than the early May seismic tremor, but it is still there. As a result of that, the lava level in the channel goes down, and the bulk effusion rate goes down, and the velocity of the lava in the channel goes down. But when the fountains start to die away, well, they don't die away, but as they start to wane and come back down in height, the SO2 kind of stays trapped in those fountains a little longer. The seismic tremor goes down. The lava level in the channel goes up because all of that material, instead of going up and releasing the gas, is now coming out and over into the spillway. So the bulk effusion rate goes up and the velocity in the channel goes up. And this happens on the order of minutes. Roughly every 10 minutes or so you can see this change happen. Sometimes it's more dramatic than others, but this seems to happen on a cyclic pattern, just like gas pistoning. So here's a video of that. This is the low flow time where the fountains are high just off the screen, higher. They got about 50 meters around this time. And then you'll see it's starting to speed up again. And the lava is reaching higher because the fountains are dropping and is coming down the spillway faster. So it banks up and builds up these ramparts in the back here. So we can use gas pistoning to help explain this behavior in the lava channel that for a while during the eruption was kind of enigmatic for us. All right, and then our last question. Why did the Fissure 8 lava delta not collapse? I've been asked that many times. And I'm not sure we entirely know the answer, but I'll tell you where my thoughts are on this. This is something that my colleague Mike Zoller and I are working on right now. And to refresh your memory about deltas, we're going to jump back to 61G in 2017. When a Pahoehoe lava delta comes, it has to dribble over a cliff and then find the seafloor and start building itself up. And it does this basically by putting layer on top of layer on top of layer. And when it interacts with the water, it makes this fine sediment base as well. So it may have some lava flow in there and it may be some particles and a mix thereof. Whereas up top, it's all lava flows. As you can imagine, this gets heavy, and this is not very stable. So at some point, you develop a zone of weakness. And that manifests itself the surface up here as cracks in the delta. Now, just because we see a crack, we don't know how deep it extends. And all we know is that this land is unstable, and because it's cracking, it might fail sooner than later. When it does, it can either fail partially or in whole and take some of the previous sea cliff with it. And either way, when hot water from the ocean entry interacts with freshly exposed lava, you get big explosions. And they have hurt and killed people in Hawaii in the past. So what's different about 2018? Why didn't that happen? Let me back up. These graphics, I love them. They're wonderful. But I will note that they are 2 times height exaggerated. So I've redrawn it to be 1-to-1. And I've drawn this one from Kapoho to also be 1-to-1, so that we're comparing apples to apples here. You'll notice that at the 0 marker, which is where the coastline is, a Pahoehoe Delta has a pretty steep drop, and it has to build itself up until it reaches a good equilibrium spot. And it's still oversteepened here, if you notice. This arrow just implies that the current could erode some of this more fine-grained sediment and help undermine the delta. If we look at the Kapoho Bay and the first part of the delta that formed there, it's pretty darn flat. So I'm not worried about lava that filled in the bay collapsing, per se. It's not until it reaches the edge of the shelf and drops down to deeper levels in the ocean that it starts to approach this slope. But even so, on this slope, this lava flow, even though it's not off flow, is going to behave a little differently than the Pahoehoe, which is oversteepened onto this slope. So I think inherently, Pahoehoe might be more inclined to collapse as a delta than A'a flows. Now this is, we still have more work to do on this to support this, but we haven't seen any cracks form in the Kapoho A'a delta, nor did we during the eruption. Maybe one crack, but we typically didn't see the features that we were looking for to say a collapse is coming in, who knows, days, weeks, months, but the cracks are there. The other interesting thing that we noticed, and I have some pictures on the next 2 slides for you guys, is that right here, there's a little bit of breakouts at the ocean entry that kind of does one of these Pahoehoe things, and it overlaps on top of the A'a. But in general, the channel would just flow straight into the ocean. And that told me that it's entering some protected, it's protected its top somehow, that it's not interacting with the water. It's not exploding. It did on a few occasions, but fairly rare for the whole eruption. And it went out. This is a real bathymetry profile of pre-eruption and from boats who came by to do surveying. So it went out, 2.5 kilometers away from where the shoreline starts dropping off, or from the edge of the old coastline. And so the thought is, where is all this material going? And many of us at HVO asked that. Where is all this material going? And why isn't it exploding when we know these little tiny things can cause explosions from Pahoehoe deltas? And so what I realized is that this is actually inflating and kind of lifting up out of the sea. It didn't do that all the time, but the next slide I'll show you an example where we did see it lift up. We saw that twice actually, and it was fairly interesting. But the point is that this is a cohesive flow as it extends underwater, whereas the Pahoehoe is just onlapping layers and layers. And so perhaps this is actually a more stable delta anyways, even though it already has a more shallow slope to begin with. Okay, this is shortly after the lava entered Kapoho Bay. We're going to focus on this feature here. It's got a peak in the middle and 2 dips. We're going to try to track that through June. So here we go. Put an arrow there to help. It's going to get more and more subtle as time goes on, but it's here. And I want you to focus on this next lobe that came out and formed a new part of the delta. And we're going to look at what happens to the water in between these two. So in this picture down below, it's here. And then on June 11th, a few days later, it's here. And on June 14th, it's isolated from the ocean, and it's actually slightly higher than the ocean. Then, yes, I added the other slide. June 15th, not much change. June 22nd, it's evaporating away, and it is 1 or 2 feet above sea level at this point. So that's something that I don't think we've ever seen in a Pahoehoe Delta, where it kind of lifts up from the sea as opposed to piling on top and going into the sea and diving down. And then the last example I have of this is from July, where we were doing our routine flights. At this point, we weren't allowed to fly over the open ocean because there was such a long stretch where we had no emergency landing that we just decided it's not worth it. But this was right on the edge. And this was the coastline the day before, and then suddenly this quote unquote island appeared. But really, this just kind of rose up. It's connected to the delta underneath. There's only a couple feet of water here, and it's erupting lava. It's still the fissure 8 lava. It's just come down through the delta underneath and back up. And so again, we have another example of something kind of rising up as opposed to piling on top and diving down. So some possible insights from last year that we're going to keep working on for this year is that the submarine slope was shallower in Kapoho for that delta, and perhaps deltas not only grow by onlapping, but they also grow by inflating their core. So maybe this is more stable. There's some more work that needs to be done, but that's a potential interesting insight into how lava deltas work. And with that, oh, I forgot the Kokis were in this video. I would love to thank you for joining me and HVO tonight. We really enjoyed serving the community, and we look forward to doing that in the future. Regardless of where our new home is, it'll be on this island. And we enjoy working with you guys. A big thanks to Civil Defense and the Puna residents for still welcoming us into your communities and letting us take measurements. And also thank you to Janet. She does a great job organizing all this stuff for us, and it's a lot of fun for us to give these talks, but she's like the unsung hero of all of this stuff. So thank you, everybody, and I'll take your questions.